Hey, this is going to be played in fast motion so that it's a short video. You should still be able to understand everything. This is going to explain how to do some of the most common things you'll need to do when analyzing algorithms in bigO. I hope it helps. And forgive my voice, I'm losing it. I don't know if you'll be able to tell.
I'm going to talk about bigO when you have formulas like 3n plus 4n squared minus 5, and you want to figure out whether that's big theta of what. Since it's got a bunch of terms added, we're going to look at each term by itself and throw away the constant, because for bigO, the constants don't matter. So, the 3, the 4, and even the 5 can get thrown away. If that confuses you, that's really 5n to the 0, which is 1. Right there. Then once you've done that, you know that each term is big theta of whoever wins, and those all have exponents, either 0, 1, or 2. The highest exponent is going to be the one that wins among the terms that are left. So whenever you have a polynomial like this, it's going to be big theta of the highest order term. Let's look at a different thing. We have 3 times n plus 1 plus n squared, all in parentheses, and that's big theta of what? If you're not very quick at this, you can just distribute that out, and then you get a polynomial here. So 3n squared minus 3n plus 3n cubed. You get rid of the 3, giving you n squared. You get rid of the negative 3, giving you n. I'm sorry, that's a positive 3. And then you get rid of the 3 in front of n cubed. So we're comparing n squared to n to the first to n cubed, and n cubed wins because it's got the highest exponent. 8n plus 5 times the log of n. So this one has logarithms, and we're going to add in 2 times n times the log of n. And we want to know what that's theta of. We have, get rid of the constant, we have n. Get rid of the constant, and we end up with log n. Remember big theta, no constants. And here, get rid of the 2, and we have n times the log of n. So we compare n to the log of n, and we want to know who wins. So it kind of helps to realize that log of n is really n to the 0 times the log of n. And we're comparing n to the 1 to n to the 0. And still, the highest exponent wins. We don't think about logarithms unless there's a tie. So here's a case where we have n to the 1 times the log of n, and we decide what's the higher order term. But they're tied, n to the 1 to n to the 1. And log of n is just a tiebreaker. It only even matters if the exponents match. So in this case, they did, and we end up with n times the log of n being the answer. So in general, we have n to the k, and we have n to the j. The winner is always going to be the higher exponent. So in this case, n to the k is order n to the j, if j is greater than or equal to k. And the log of n, if it's in there anywhere, is just a tiebreaker. So n to the k is order n to the k times the log of n. So the log of n beats n to the k, but n to the k log n is going to be big O of n to the k plus epsilon, and that's true no matter how small epsilon is, as long as it's greater than 0. So the exponents overpower the logarithms. We have an equation here. We have n log n plus n squared plus the log of n. And to help us out, you can think about what the exponents are. And the highest exponent is n squared, and that wins just by the exponent. Here's another one. We have n squared plus n squared log n, and we're checking to see what that's theta of. The exponents tie, so we need a tiebreaker, and log of n is the tiebreaker. It's going to win. And we end up with n squared log n. So here we have another formula. We're looking at 3n squared plus 4n log n plus 3n squared times the log of n. But this time the log is base 5 in the last term. So the first one is 3n squared. That's just n squared. We throw out the 3. 4n log n is just n log n. We can throw out the 4. And 3 times n squared, log base 5 of n, is really just n squared. And for that logarithm, it doesn't matter what the base of the logarithm is. That expression is the same as n log n. We don't need to specify the base. And if we think about the exponents, if we compare n squared to n log n, a 2 for n squared beats a 1. And now we've got that n squared, which is the winner of the first match, compared to n squared log n. That log n is a tiebreaker. So this whole expression is n squared log n. So these formulas I've been giving you are pretty helpful when you're given a polynomial or a polylogarithmic thing, a mixture of exponents and logarithms. But what happens when you throw something strange in, like a cosine? I don't expect you to have many algorithms whose runtime involves a cosine, but it helps illustrate a point. We have a term here involving the cosine. So n squared is multiplied by 1 plus the cosine of x, which just gives us a periodic function. 1 plus the cosine of x goes from 0 to 1 to 0 to 1. If we take 1 plus the cosine of x and multiply it by n squared, we get a weird function which is sandwiched in between the function which is constant at 0 and the function which is n squared, and just wiggles back and forth between them. So it touches 0, then it touches n squared, then it touches 0 again, goes back and forth. So what is that big theta of? Well, I'm just going to wait on that. We can tell where it's bounded above. So big O is when it's less than or equal to, so it's always bounded above by n squared. And it's always bounded below, but not by n squared. It's bounded below by a horizontal line, a constant. So it's big omega of 1. Since big O and big omega don't match, they don't intersect, it's not big theta of anything. So this whole expression is going to be big O of the larger of those two things. So we're comparing n to n squared and n squared 1. For big omega, we look at the two omega terms. It's either big omega of 1 or big omega of n. And since n is bigger than 1, it's big omega of n. So even though it's the lower bound, it's the largest lower bound. Thank you for watching my clip. Goodbye.